Well, so last time we discussed about chain reaction, okay? Chain reaction. An example of chain reaction is hydrogen bromine reaction. Hydrogen reacts with bromine to form HBr, hydrogen bromide, okay? Chain reaction. We have already said that uh, chain reaction takes place in three or four different steps. One is chain initiation, okay, chain initiation. The other is chain propagation, okay. Then chain inhibition step, then termination, okay, termination step. Sometimes this step inhibition may be absent, or we may not consider this step. Okay, so in that case, we can say that chain reaction consists of three steps: initiation, propagation, and termination. Okay, so chain reaction. Then we have discussed hydrogen bromine reaction in detail, okay, and we have found out the rate of reaction using steady state approximation method, okay. Then uh, let us discuss today that chain reaction may be mainly of two types. Chain reaction may be of two types. One is chain reaction two types. One is branching chain reaction, branching chain reaction, the other is non-branching chain reaction. Non-branching chain reaction, okay, two types. So we talked about these two types, okay. Now example of non-branching chain reaction is hydrogen bromine reaction. One example of non-branching chain reaction is hydrogen bromine reaction. Okay. In non-branching chain reaction, what happens? Non-branching chain reaction, what happens? In the propagation step, one chain carrier is destroyed and only one chain carrier is formed. One chain carrier is destroyed and only one chain carrier is formed. Okay? If that happens in the propagation step, then it is a non-branching chain reaction. Okay? Non-branching chain reaction. One chain carrier is destroyed and only one chain carrier is formed in the propagation step. Okay, non-branching chain reaction. Now, what is branching chain reaction? What is branching chain reaction? In case of branching chain reaction, one chain carrier is destroyed and more than one chain carrier is formed in the propagation step. I repeat, one chain carrier is destroyed and more than one chain carrier is formed in the propagation step. That is called branching chain reaction. Okay. An example of branching chain reaction. Example of branching chain reaction is reaction of hydrogen and reaction between hydrogen and oxygen to form water. Okay, this is an example of branching chain reaction. Okay, so this reaction takes place within the temperature range 450 degrees Celsius to 600 degrees Celsius. Okay, and pressure range is say 1 millimeter to 10 atmosphere, nearly 10 atmosphere. So within this temperature range and within this pressure range, this reaction takes place. Now you know 760 millimeter of mercury, 760 millimeter of mercury. That is equivalent to 1 atmosphere. That is 1 millimeter, this is mercury, okay? 1 millimeter mercury. So 760 millimeter of mercury is equivalent to 1 atmosphere. So you can convert this. So within this pressure range and within this temperature range, this reaction takes place. Okay. Now, what is the mechanism of this reaction? What is the mechanism of this reaction? So mechanism involves 26 different steps. Okay, 26 different steps. Okay, have been proposed. I am not going to write all those steps. I will write only some steps. Okay. Now, this is chain reaction. So, it will consist of chain initiation, propagation, then termination. Okay. Now, what is the initiation step? Initiation step may be like this. Say H2 plus M. From that, we are getting this hydrogen radical and M. Now, what is M? It is some species present in the reaction mixture. Okay, some substance present in the reaction mixture. Okay. Similarly, it may be like this also. 2 oxygen radical plus M. Okay. Then maybe this hydrogen plus oxygen. From this we are getting this radical, then this radical. Okay. So these are the different initiation steps. Okay. Next is propagation step. Okay. Now propagation step may be like this. Okay. This radical reacts with hydrogen to form H2O plus H plus. Okay. Now maybe it reacts with oxygen to form OH H. Okay. Then maybe this OH plus O. This is O. OH plus O. This is O. O plus H2. OH plus H. So these are the different propagation steps. Now in this propagation step, you see one chain carrier. These are the chain carriers. Hydrogen radical, oxygen radical, hydroxide radical. These are the chain carriers. Okay. So one chain carrier is destroyed and only one chain carrier is formed. Okay. This propagation step is known as straight chain propagation step. Straight chain propagation step. Propagation. Okay. But here you see one chain carrier is destroyed, more than one chain carrier formed. One chain carrier is destroyed, more than one chain carrier formed. So these are the two propagation steps, and these are known as branching chain propagation. Branching chain propagation. Okay. Branching chain propagation. So you see, branching, more one chain carrier is destroyed and more than one chain carrier formed. Okay. Then termination. Termination. Now termination of chain reaction may take place in two ways. Termination of chain reaction may take place in two ways. One is called gas phase termination. Gas phase termination. What is gas phase termination? Here you see this is a chain carrier. This is chain carrier. It reacts with O2 and M. It is some species present in the reaction mixture. Okay. From that we are getting HO2 radical and M. And this is known as hydroperoxyl radical. Hydroperoxyl radical. Okay, hydroperoxyl radical. So this is formed. Okay. Then this species is adsorbed on the wall of the container. This species gets adsorbed on the wall of the container to form some stable species. So that the reaction stops, terminates. Okay. Now this reaction takes place in gaseous medium. This reaction takes place in gaseous medium. So it is gas phase termination. But this is not gaseous, because this is solid. This is gaseous, this is solid. Okay. So this reaction does not take place in gaseous medium. Okay. So this species gets adsorbed on solid wall. Okay, to form stable species. So this is known as gas phase termination step. Okay. So as I have said, termination of chain reaction takes place in two ways. So this is one way. Second way is that surface deactivation. Surface deactivation. Surface deactivation. What is surface deactivation? Here say this radical. So all these radicals get adsorbed. Gets adsorbed on the wall of the container. Wall of the container to form some stable species. Okay. So there is no other reaction. So these chain carriers get adsorbed on the wall of the container. That is, they get adsorbed on the surface of the wall. Adsorption is surface phenomenon. So they get adsorbed on the wall, that is surface. Okay. So this is known as surface deactivation. Okay. So since all the chain carriers are removed, so the reaction cannot proceed further. That means the reaction terminates. Okay. So this is known as surface deactivation. So these are, though there are 26 different steps, we have mentioned only a few. Only a few. So this is the branching chain reaction. Okay, this is the branching chain reaction. Now, let us discuss about in general. In general, let us discuss about kinetics of kinetics of chain reaction. Okay, chain reaction. In general, now we will discuss in general kinetics of chain reaction. Okay. Now, a chain reaction may be a general chain reaction. Say, this is a chain reaction. This is a chain reaction. This is reactant product. Okay, this is chain reaction. So, what is the mechanism? What is the mechanism? Okay, mechanism may be like this. Say, from reactant, this is the rate constant, we are getting chain carrier. So let me write chain carrier like this. Okay, chain carrier, and this is the initiation step. Initiation step. Okay, then the chain carrier reacts again with the reactant to form the product plus chain carrier. Let me write here alpha number of chain carriers. Okay, alpha number of chain carrier is formed. Now if alpha is 1, what happens? One chain carrier is destroyed and only one chain carrier is formed. Then this will be non-branching chain reaction. But if alpha is greater than 1, say 2, 3 like that. If alpha is greater than 1, then one chain carrier is destroyed and more than one chain carrier is formed. Then this will be branching chain reaction. Alpha is 1, non-branching chain reaction. Alpha is greater than 1, branching chain reaction. And this is propagation step. This is propagation step. And then termination. In the termination step, chain carrier must be removed. Okay, chain carrier must be removed. So chain carrier is destroyed. Okay, let me write like this. Chain carrier is, okay, destruction. Okay, that means chain carrier is destroyed. Destruction. Okay, destruction. Chain carrier is destroyed. So this is the termination step. Termination step. This is destruction. Okay, destruction. Chain carrier is destroyed. That is the termination step. So chain carrier is destroyed means the reaction stops, terminates. Okay. So once again here A is the reactant, P is the product, R star, this is the chain carrier. Okay. And alpha is the number of chain carriers. Okay, number of chain carriers. Now from this mechanism, I can write dr by dt. Okay, from this mechanism, I can write dr by dt. I can write dr by dt. Okay, if I write this, what I get? So here you see this is formed, so this will be K1 into concentration of A. Okay, K1 into concentration of A. Here you see this is removed, lost, and this is formed. You see, this is removed, this is formed. So there will be two terms, one for removal, that will be minus this into this, and one for production, that will be plus. There will be two terms, and this is of course one term, this is removed. Okay, so let me write dr by dt. So this will be equal to k1a, k1a. Okay, this is all right, k1a, then minus k2ar, okay, then this will be plus alpha into this is alpha into k2ar, okay, then minus k3r, okay. Now do you understand this, why this is alpha into this? Okay, because you see, if you write here, for this, if you write r, r equal to 1 by alpha into dr dt. Okay, from this if you write r will be equal to 1 by alpha into dr dt. So dr dt will be equal to alpha into r. Okay, now what is r? r equal to k2 a, this r equal to this. So dr by dt will be equal to alpha into this. Okay, so this is alpha. Okay, so we are getting this. Okay, now according to steady state approximation, so dr dt, because this is nothing but intermediate, 0. So what? So this is a number 1. So from 1 what we get? Say, let me write it like this. K1a is equal to K2a plus alpha into K2a, minus K3 so this is this, and this will be minus, this will be minus, this will be plus. Okay, because I'm taking these things this side, I'm taking these things this side, so this will be minus, and this will be plus, this into r. Okay, let me use this bracket just to remove confusion. Okay, let me use this bracket, or or so that is this. So this is equal to K1A, K1A, sorry, K1A divided by 1 minus alpha, 1 minus alpha K2A plus K3, plus K3. Okay, or we can write it like this, K1A minus alpha minus 1 minus alpha minus 1 K2A plus K3 plus K3. So we can write like this. So basically what we are doing, we are finding out an expression. We are finding out an expression for the concentration of the chain carrier. Okay, for the concentration of the chain carrier. Now here K3, what is K3? This is the rate constant of the termination step. Now we have already said termination may take place in two ways. One is gas phase termination, the other is surface deactivation. So termination may take place in two ways, gas phase deactivation and surface deactivation. Okay, so we can write it like this, Kw plus Kg. What is this? This is the rate constant for surface deactivation. This is the rate constant for surface deactivation, and this is the rate constant for gas phase deactivation. This is the rate constant for gas phase deactivation. Okay, so we can write like this, K3 equal to this. So from 2 I can write this is equal to K1A minus alpha minus 1 K2A plus Kw plus Kg. I can write it like this. Okay, this is a number 3. I can write it like this. Now why I am find out an expression for the concentration of chain carrier, because the rate of the reaction mainly depends on the concentration of the chain carrier. Rate of the reaction, you see, rate of the propagation step. Okay, rate of the propagation step depends on the concentration of the chain carrier. That is why we have found out an expression for the concentration of the chain carrier. Now here you see, when say case 1, okay, case 1 may be say alpha equal to 1. We know if alpha is equal to 1, that is what we get? We get non-branching chain reaction. If this is the case, now you see what is the concentration of R. What is the concentration of R? This will be equal to, now this will be 0, so this will be equal to K1A by Kw plus Ka. Okay, so uh, so this is the expression for the concentration of chain carrier for alpha is 1 means it is non-branching chain reaction. Okay, that is non-branching chain reaction. Okay, this will give us non-branching chain reaction. So what we get for non-branching chain reaction, concentration of chain carrier is equal to the ratio between the rate of formation of chain carrier and rate of destruction of chain carrier. Rate of formation of chain carrier and rate of destruction of chain carrier. So R is concentration of R is equal to the ratio between the rate of formation of chain carrier, this is the first step, and rate of its destruction. Okay. Now case 2. Case 2. Say alpha is greater than 1. We know alpha is greater than 1 means it is branching chain reaction. This is branching chain reaction. Okay, branching chain reaction. Now alpha is greater than 1, that means more and more chain carriers, are produced. And eventually it may happen that K2A alpha minus 1 is equal to Kw plus Kg. So alpha is greater than 1, obviously branching chain reaction. Okay, that means when alpha is greater than 1, production of chain carriers will be high. Okay, so more and more chain carriers are produced, and in the long run it may happen that this is equal to this. Now when this is equal to this, you see, when this is equal to this is negative, this is equal to this, that means minus this plus this, that means it becomes 0. Okay, it becomes 0, that means concentration of R becomes equal to this by 0, that means infinity. Okay, infinity. And since we have already said what is the rate of the propagation step, rate of the propagation step is proportional to R. Okay, so you see this becomes very high, concentration of R becomes very high, so rate of reaction, rate of reaction becomes very high. Okay, becomes very high. becomes very high. And when rate of reaction becomes very high, then explosion takes place. Explosion occurs. Explosion takes place. You see, explosions take place. Okay? So this is the thing. So in case of branching chain reaction, explosion takes place. Branching chain reaction, explosion takes place. Why explosion takes place? Because rate of reaction is very high. Very, very high. When rate of reaction is very, very high, explosion takes place. Okay? So this is so thus in branching chain reaction, explosion takes place. Okay. So basically this is all about your chain reaction. Okay. So we have discussed about chain reaction. Now let us discuss another thing, which is uh, factors affecting rate of reaction. Okay. Factors affecting rate of reaction. Rate of reaction. What are the factors which affects speed of reaction? Okay, speed of reaction. Number one is nature of reactant. Number one is nature of reactant. Nature of reactant means if the reactant changes, obviously speed of the reaction, that is rate of reaction, will change. For example, say let us see this example. Say this reaction, chlorine. Okay, you may get this. You may get this. Okay, this reaction takes place even in diffused light. Diffused light means not direct sunlight, but say inside the room. Inside the room, you don't get direct sunlight. So this reaction may take place inside the room. Okay, but if you consider this, say bromine. Okay, CH3Br HBr. Now here direct sunlight is needed. Okay, that means, so here condition of the reaction is nature of reactant changes. So condition of reaction changes. Okay. Again, if you take this iodine, now this reaction does not take place under normal condition. This reaction does not take place under normal condition. So you see, as the nature of reactant changes, so rate of reaction changes. Similarly, let us take another example. Say sodium plus water. You will get sodium hydroxide and hydrogen. Okay. Now you just put a piece of sodium in water, reaction will take place. Okay. Similarly, same. Okay. Similar reaction takes place. But compared to this reaction, speed of this reaction is much higher. Okay. So as soon as you put a potassium in water, it will catch fire with explosion. Okay. There will be sound. Okay. There will be sound and it will catch fire immediately. That means speed of this reaction is much higher than the speed of this reaction. Okay, so you see, as the nature of reactant changes, rate of reaction changes. Second is concentration of reactant. This you already know because R is proportional to the concentration of the reactant. You know this. Okay. Then there is one factor called temperature. Temperature. Okay. We will discuss the effect of temperature a bit later. Okay. Then catalyst. Catalyst. So you know catalyst increases rate of reaction. Okay. You know this. So catalyst plays a role in increasing the rate of reaction. Okay, you know this. Now, effect of pressure may be there mainly in case of gaseous reaction. Mainly in case of gaseous reaction. Effect of pressure may be there. Okay. So you see there are so many factors which can affect the rate of reaction. Now let us discuss the effect of temperature. Okay, effect of temperature. Effect of temperature. Now it is observed that if the temperature is increased by 10 degrees Celsius, the rate of reaction increases twice or thrice. Okay. Suppose this is the we have a reaction. Suppose we have a reaction like this. So first say we are doing the reaction at T degrees Celsius. Okay. First we are doing the reaction at T degree Celsius, and at T degree Celsius, let the rate be RT and rate constant be KT. Okay. Then say we are increasing the temperature, keeping concentrations constant. We are increasing the temperature by 10 degrees Celsius. If it is 25 degree, then it will be 35 degree. Okay. In that case, rate is say RT plus 10 and rate constant is say T plus 10. Now what is observed? If we increase the temperature by 10 degrees Celsius, the rate increases twice or thrice. That means RT plus 10 by RT, that is equal to KT plus 10 by KT, that will be equal to 2 or 3. Okay, and this is known as the temperature coefficient. Temperature coefficient. Temperature coefficient of reaction. Okay. Now from this we get some idea that if we increase the temperature by 10 degree, rate may increase twice or thrice. But when twice, when thrice, we don't know. If we just write like this, okay? If we just write like this, we don't know when twice, when thrice, that we don't know. Again, if we increase the temperature by say 5 degrees Celsius, not 10 degrees, 5 degrees Celsius or say 15 degrees Celsius, what will happen? So we don't get answer from this. Okay. Now a better relation between temperature and rate constant was given by Arrhenius. So Arrhenius gave a better relation between rate constant and temperature. Okay, and the equation is this: K equal to A into e to the power minus EA by RT. EA by RT. Okay, so this is the Arrhenius equation. This is known as Arrhenius equation. Okay, here this is the rate constant of the reaction A. A is called the pre-exponential factor or frequency factor. Pre-exponential factor or frequency factor. Then R, you know, molar gas constant. T is the absolute temperature, Kelvin temperature, and EA is the activation energy. EA is the activation energy. Okay, EA is the activation energy. Now, what is activation energy? Let me tell you like this. Say, suppose this is the reaction. Okay, say this is the reaction. This is the reaction. Now you know any matter possesses some amount of energy, okay, which we call internal energy. So it has energy, internal energy, it has internal energy, it has internal energy, it has internal energy. Okay? So when we say energy of the reactant means energy of A plus energy of B. Similarly, energy of product, that means energy of C plus energy of D. Okay? So they have internal energy, or we can say they have enthalpy. You remember enthalpy? Enthalpy equal to U plus PV. So enthalpy. Okay? So the reactant, suppose this is okay, let me write it like this. Say this is the energy of the reactant. This is the energy of the reactant. This is the energy of the reactant. Say, let me write as enthalpy. Enthalpy of the reactant. Enthalpy means energy. So this is the enthalpy of the reactant. So suppose as we move up, energy increases. As we move upwards, energy increases. That means enthalpy increases. Energy increases, enthalpy increases. Okay. Now, and suppose this is the energy of the product. This is the energy of the product. Now here what we find, energy of the reactant is greater than energy of the product. Okay, here we find that this is greater than this. Energy of the reactant is greater than energy of the product. So when this happens, so this must be an exothermic reaction. In case of exothermic reaction, energy of reactant is greater than energy of product. Okay. Now in case of endothermic reaction, energy of product will be more than energy of reactant. But thing is that for the reaction to take place, for this reaction to take place, first energy of the reactant must increase. That means the reactant must get this much energy in excess. This is the energy of reactant. So this is the extra energy. The reactant must have to form the product. Reaction to jodi hobo lage, reactant of a extra energy khini lagiboi. And this is the minimum energy. Yatke jodi besi energy pae, obviously reaction will take place. But yatke jodi kom energy pae, reactant jodi yatke kom energy pae, reaction to no hobo. Okay? Reactant jodi এইখিনিতকে কম এনার্জি পায়, reaction to no hobo. Okay? The reaction will not take place if the reactant gets less energy than this. Okay? But if the reactant gets more than this energy, obviously reaction will take place. So this is the minimum energy. The reactant needs to form the product, and this is known as the activation energy. Okay? What is activation energy? It is the minimum energy. The reactant needs to form the product. Okay? Or we can define it like this. This is the minimum extra energy required by 1 mole of the reactant to undergo chemical change. Okay? Minimum extra energy. Okay? ইয়াতকে যদি কম এনার্জি পায়, ৰিয়েকশ্যনটো নহ'ব। মিনিমাম এইখিনি এনাৰ্জি লাগিবই, তেতিয়াহে ৰিয়েকশ্যনটো হ'ব। চ' দিছ ইজ কল্ড দি এক্টিভেশ্যন এনাৰ্জি। অ'কে? চ' এটা কমন এক্সাম্পল আছে। পাৰ্কত তুমি নিশ্চয় খেলিছা এনেকুৱা শ্লাইডিং। হিয়াৰ ইউ চিট, দেন ইউ কাম ডাউন শ্লাইডিং। অ'কে? শ্লাইডিং পাৰ্কত নিশ্চয় তোমালোকে খেলিছা। সেই ইয়াতে তুমি বহিলে তুমি পিছলি আহা। অ'কে? নাও ফৰ দি বেবী, বাচ্ছা এটাৰ কাৰণে প্ৰব্লেমটো কি? টু চিট হিয়াৰ। অ'কে? বাচ্ছাটোৱে যদি ইয়াত বহিব পাৰে, তেনেহ'লে ৰক্ষা নাই, সি পিছলি আহিবই আৰু। Similarly, the reactant must have this energy. Only then it can form the product. That is the activation energy. Okay? So this equation, let me write this as number 4. Let me write this as if I take log, what I get? Say ln k. Once again, what is ln k? Log to the base ln k equal to log to the base e k. Okay? So ln k equal to ln a plus means it will be minus EA by RT. Okay? If I take log, I will get this. Okay? Now, if I do this same reaction at different temperatures, say at T1 and T2, same reaction performed, same reaction performed at two temperatures, performed at two temperatures, T1 and T1 Kelvin and T2 Kelvin. Then I can use this, what I can write? ln K1 equal to ln A minus EA by R T1 and ln K2 ln A minus EA by RT2. Okay, we can write. So this is say 5 and this is 6. Now if we do this 5 minus 6, what I get? ln this minus this, that means ln K1 by K2. So this will be 0 and this will be EA by RT2 minus EA by RT1, and that is equal to EA by R 1 by T2 minus 1 by T1. Okay. Or this is ln K, this is equal to 2.303 log. Now it is log to the base 10. Log to the base 10 K1 by K2 equal to EA by R 1 by T2 minus 1 by T1. Now from this what we can find out? If we know rate constants, at two temperatures, K1 and K2 at two temperatures T1 and T2, then we can find out the activation energy of a reaction. We can find out that. Okay. Say, suppose you have been asked a question like this. The rate of a reaction increases twice as the temperature is increased from 27 degrees Celsius to 37 degrees Celsius. Find activation energy. Okay, find activation energy. So very simple, you can easily solve it. So if you put that K1 equal to say K, then K2 will be equal to 2K. Okay, because rate increases twice and temperature is 27 degrees Celsius, that means 300 Kelvin, and T2 is equal to 310 Kelvin. So you just put here 2.303 log 2K by K equal to EA by R. R means 8.314 joule per Kelvin per mole into 1 by 310 Kelvin minus 1 by 300 Kelvin. Okay, I can take Kelvin common. I can take Kelvin common. So Kelvin will cancel. So what do we get? 2.303 log 2. Okay, log 2 equal to 0.301. Okay, then EA is equal to 8.314 joule per mole. Okay, Kelvin cancel, joule per mole, and just simplify 310 into 300. Okay, 310 into 300, then this is 300 minus 310 minus 10. Okay, minus 10. Oh, sorry, I have committed one mistake. This is K1 is K, this is 2K. Okay, K1 is K, this is 2K. So not this. This is log half. Okay, log half this. Now I can write it like this: 2.303 log 2. Then this will be minus equal to EA by 8.314 joule per mole into minus 10 into 300. So minus cancel. Then you just simplify and find out. This is a 0.301. So you just find out. A unit will be joule per mole. Okay. So this is how we can solve it. Activation energy we can find out. So this is very simple, no difficulty at all, I think. Now from this expression, okay, now from Arrhenius equation, what is Arrhenius equation? Arrhenius equation is this: e to the power minus EA by RT. I can write it like this: e to the power EA by RT. Okay, I can write it like this. Now here you see, if temperature increases, if T increases, what happens? T increases means this decreases. That means this decreases. T increases, so this decreases. That means this decreases, so K increases. Okay, that means as temperature increases, rate of reaction increases. But if activation energy increases, what happens? If activation energy increases, what happens? This increases, that means this increases, so K decreases. Okay, that means as activation energy of reaction increases, rate of reaction decreases. Okay, so this information we get. Now what does a catalyst do? What is the function of the catalyst? Okay, so function of catalyst. We know catalyst increases the rate of reaction. Catalyst increases the rate of reaction. How? How a catalyst increases the rate of reaction. Okay? How a catalyst increases the rate of reaction. Generally, what we say? We say that catalyst does not take part in a reaction. We say like this. I repeat, generally what we say? We say that a catalyst does not take part in a reaction. But that is not true. That is wrong. A catalyst takes part. A catalyst takes part in the reaction. Okay? But the amount of the catalyst remains the same. That means amount of catalyst before the reaction equal to amount of catalyst after the reaction. So the amount of catalyst does not change. It does not mean that the catalyst does not take part in the reaction. A catalyst does take part in the reaction, but the amount does not change. So let me write, a catalyst does take part in the reaction. Let me show you here. I have already written, say this here you see, this is the catalyst. It takes part in the reaction, but we are getting back the entire amount of catalyst. Catalyst takes part in the reaction, but we get back the entire amount of the catalyst. Okay, so it is not true that the catalyst does not take part in the reaction. Okay, suppose we have a reaction like this. So this reaction may take place in absence of catalyst, and of course it will take place in presence of catalyst. এই রিয়েকশনটো ক্যাটালিস্ট নাথাকিলেও হ'ব, কিন্তু ক্যাটালিস্ট নাথাকিলে স্পিড কম হ'ব, ক্যাটালিস্ট থাকিলে স্পিড বেশি হ'ব. Okay, that is the difference. Okay, now you see, in absence of catalyst, once again, in absence of catalyst, the reaction will take place. And the mechanism, it will have some mechanism. Some mechanism is there. Okay, some mechanism is there. But in presence of catalyst, mechanism will be different. Mechanism is different. Why? Because catalyst takes part in the reaction. There is no catalyst, so mechanism is different. There is catalyst, same reaction, there is catalyst, mechanism is different. Why? Because catalyst takes part in the reaction. Okay, that means we can say that in presence of catalyst, the reaction follows a different path. In presence of catalyst, the reaction follows a different path. Let me show you here. Okay, say this is the energy of the reactant. So this is the energy of the reactant. and this is the energy of the product. This is the energy of the product. Okay, energy of the product, and this is the activation energy. This is the activation energy. Activation energy. This is activation energy. Okay, this is activation energy. And suppose this is the part of the reaction. This is the part of the reaction. This is the part of the reaction in absence of catalyst. Okay, this is the part of the reaction in absence of catalyst. There is no catalyst, so this is the part of the reaction in absence of catalyst. This is no catalyst. No catalyst. Okay, now same reaction in presence of catalyst. So in presence of catalyst, the reaction may follow this path. May follow this path. May follow this path. So mechanism is different. That means path of the reaction is different. Now here what happens? Here activation energy is, this is the activation energy. Say this is say E activation energy in presence of catalyst. In presence of catalyst. Okay. Now you see, in presence of catalyst, the reaction follows a different path where activation energy is less. I repeat, in presence of catalyst, the reaction follows a different path where activation energy is less. And we have already seen activation energy less means rate of reaction will be more. Okay? So you should not say that a catalyst reduces the activation energy of a reaction. One should not say like that. What we should say? In presence of catalyst, the reaction follows a different path where activation energy is less. Okay? In presence of catalyst, the reaction follows a different path where activation energy is less. And activation energy is less means speed of the reaction will be more. So that is the function of the catalyst. Okay. Now regarding catalyst, you have another chapter in this syllabus. There we will discuss about the function of catalyst in detail. Okay. So today what we have discussed, basically we have discussed about chain reaction and factors affecting the rate of reaction. Okay, we have discussed about this, and we have also discussed about the effect of temperature on rate of reaction. Okay, so let us stop here. Next, I think within next 2 classes I will be able to finish the chapter on finish the unit on chemical kinetics. After finishing this, I will go to the unit catalysis. Okay, thank you.